right, hello and welcome to the Masterclass, Honouring Rigor in Science Through Concept-Based Inquiry. My name's Jessica Humble-Crofts, and today I'm joined by my colleague Andrea to lead this really important discussion. So our agenda today has 4 key points. First, we're going to define rigor and how we use it in our context. Next, we're going to explore the use of different sized concepts to add breadth and depth to our teaching. Then we're going to look at increasing the number of conceptual understandings in science units in order to ensure a rigorous experience. And lastly, we'll consider how concept-based inquiry promotes student ownership of learning while strengthening communication and thinking skills. Throughout the session today, as Rachel mentioned, we'll be using quite a few different concept-based inquiry strategies that can be used with students in a classroom setting. So not only do we want you to participate, but we also want you to think about, each time we use a strategy, think about how you might use or adapt it for your learning context. And we'll point them out as we go through. So before we get into it, a little bit about myself. Although I've held many roles throughout my career in education, I am first and foremost a teacher. I've spent over 15 years serving primarily as a teacher of science and mathematics in middle and high schools, in international schools across 3 continents. A few years into teaching, I began a quest to find a pedagogical method that enhanced my students' ability to transfer their understanding while still developing discipline expertise. And this purpose ultimately led me on my concept-based journey, where I became an Erickson and Lanning certified trainer. And currently I serve as the science specialist for the Concept-Based Curriculum and Instruction Institute. I also run concept-based workshops around the world, and I've spent the past few years developing a concept-based inquiry mathematics curriculum with both Rachel and Andrea. I've also been very fortunate to develop and facilitate several professional learning courses for Professional Learning International, including one about the very big importance of process across the disciplines and one on concept-based inquiry in science.
So thank you. Hello, everyone. I am Andrea and thanks for joining us today. Now, some of you might actually recognize my drawings before you recognize my face. I had the honor of illustrating Rachel French and Carla Marshall's green book there on the side, the Concept-Based Inquiry in Action. That's one of my passions as an illustrator, is taking ideas and turning them into visuals that people can understand ideas in different ways. I've also been an educator for many years, and I've had a lot of firsthand experience seeing the power of concept-based inquiry and what it can have on education in the classroom. So when Rachel asked Jess and I to host this masterclass, we actually had a lot of ideas of what we could do for this, because for the past quite a while, we had been developing the new science course for PLI, and that's going to get launched in April. So we have a lot of ideas, and we've had to just carve out a few in this hour today. Now, you might notice that Jess and I have some similarities on our resume there. So a little bit fun facts about us is we actually met many, many moons ago while working at Frankfurt International School. And although we were at different campuses and different sections, we actually ended up having a lot of different adventures together, including going to the Kalahari and working with teachers there. This is also where we met Rachel. And Rachel has also joined us in the Kalahari before. And it was about 3 years ago that Jessica and I reconnected, basically through the Concept-Based Inquiry Mathematics project, when we started developing curriculum for that. Now, we do have a lot of meetings, Jessica and I, and so we do like to discuss some of our past experiences that aren't exactly the same, like teaching at Disney World as an education facilitator, or whitewater rafting in Colorado as an Aussie, driving an ice cream truck, driving a frozen food truck, just, the things that you've done in your past lives. So before we go too much further, a copyright reminder, please do not take any screenshots or recordings of this presentation, but feel free to take as many personal notes as you want for your own understanding and growth. In fact, you might need to have a pad of paper nearby for one of our activities that we're having to do coming up. Now, like most concept-based inquiry, and at least inquiry-based learning, we do want to have some guiding questions, and here's a highlight of some of those that we're going to use throughout the masterclass today. So What do we mean by rigor and why it is important in the science classroom? How do different science concepts ensure breadth and depth in science curriculum? How does the number of conceptual understandings in a unit of study support a rigorous curriculum? And how does CBI promote student ownership of learning and enhance communication and thinking skills? We're going to jump into an activity right away. This one is called Spectrum Statements. And in a moment, we're going to put some statements up on the screen. And a lot of these statements are actually ones that Jess and I have heard as we've been talking about concept-based inquiry in science. So these are some common things that we've heard. And the purpose of this is to gauge how strongly or disagreeing, how much do you disagree or agree with the statement on the screen? So in a moment, I'm going to put it up there. You're going to decide, do you strongly agree, disagree, strongly disagree, agree, or strongly agree, and put that into the chat. You might also include a justification for why you're feeling that way. You guys ready for the first statement? Teaching conceptually in science means that teachers cover content very broadly using key concepts. Think about that. How does this statement resonate with you? Do you strongly disagree? Do you disagree, agree, or strongly agree? Put that into the chat. And if you want to put a justification in it, go ahead and explain your thinking. I see some responses in all caps. There's some very, very strong feelings. Okay. Jessica, what do you think? I think I'm seeing it kind of across the board. A lot of
it's
in the
really
middle, though.
broad, right? Mm-hmm.
Yeah, I see a lot though in the agree, disagree. Not too many super strong feelings there on that one. Okay, let's go to our next one. You guys ready? Science skills take up so much time because I must reteach them every year. How does that resonate with you? Strongly disagree, strongly agree, disagree, agree. Hey. I like someone just said, disagree. If I do it properly, yes. It takes up some time. Okay. Jacqueline says, if a school plans the development and the tools to support this across all years, then it should be revisited and billed each year. Yeah. Okay. Nice. Thank you for sharing some of those justifications for your thinking behind that. All right, we're going to try another one. There is so much content to cover, so I don't have enough time to teach conceptually. Okay, you know the drill? How are you feeling in relation to that statement?
Got a lot on the strongly disagree side now, Andrea.
All right. Yeah, a lot more there.
But some people agreeing that there is a lot of content and...
Oh my goodness, there is. I mean, what do we do, right? We do have a lot of content and it's not like it's getting smaller. In fact, it's changing and developing and there's new discoveries and inventions. So our content sometimes seems to be expanding while our time in the classroom almost seems to be getting smaller and smaller. Keep these statements in mind. We actually are going to come back to them towards the end of the class today and just have a think about how our thinking might have shifted, or maybe your reasoning might have changed, or maybe you have some more justifications for your thinking as well. So let's get to our first guiding question. What do we mean by rigor, and why is it important in the science classroom? I want to be really, really clear right here from the start. When we mean rigor, we do not mean that learning is going to be harder. Rigor in education is not synonymous with burdening students with excessive workloads, with giving them tons and tons of homework. It's not about transcending the mere act of presenting difficult and hard work or just elevating standards in hopes that students are going to actually achieve higher test scores, we do not mean that harder is better. So what do we mean? Well, it is twofold. So the first part we think about when we think about a rigorous curriculum, we're thinking about a curriculum that has breadth and depth. So it's about teaching the knowledge, skills, and understanding with breadth and depth. We need to ensure the content and skills support students in building a broad understanding of a discipline, as well as developing age-appropriate depth. The result is increasing complexity in understandings as students move through their schooling. Rigor is for every student, regardless of their level. You may have seen classrooms that seem to be a mile wide and an inch deep, students memorizing facts and just learning a bunch of algorithms, and that's the one way to do it. Or maybe the opposite, and a teacher who focuses on a few areas of a discipline intensely and sort of skips over the rest. Rigor is about finding the balance of breadth and depth. Secondly, that other side of rigor that we're talking about today is about cultivating specific attributes in students. These attributes are not only essential for academic success, but also contribute to their overall development as critical thinkers and lifelong learners. As we strive for rigor in the science classroom, we aspire to teach in ways that not only deepen understanding, but also cultivate resilient, curious, critical thinkers ready to face the challenges of the future.
Okay, now that we're clear about what rigor is and what rigor isn't, and how we're using it in our context, let's talk about how concepts and conceptual understandings can be used to ensure we have both breadth and depth in our science curriculum. Before we talk more specifically about types of concepts, though, let's use a concept formation strategy to check that we all share a common understanding of what a concept actually is. The strategy we're going to use is called is not. It's a really simple but very effective strategy to use when you want to ensure your students know the attributes or characteristics of a concept and have a shared understanding of the definition of that concept. There are actually two ways to use this strategy. Here's how we're going to use it today. We need a simple 2-column chart or T-chart, like a table or a T-chart like the one on the screen, labeled is and is not. I'll then show you individual words or short phrases and place them in either the is or the is not column. The is column will contain, in this case, examples of concepts, and the is not column will contain non-examples of concepts. As I add each word to the table, consider what all of the examples in the concept side have in common. And you can use the non-examples to help you figure this out as well. And when we've finished going through the strategy, I'm going to ask you to put your list of attributes or characteristics in the chat. Are you ready? So here's the chart with a few things already written into it, just to get a start. On the left-hand side, we have the is column, where there are things like force, translation, fission, and life cycle. These are all examples of concepts. In the is not column, we have copper, Thailand's population, 2 centimeters. And these are all non-examples of concepts. So let's add some more to this chart. Remember, it's your job to decide why the words are in the is column while others are in the is not column. So first up, we have the word pattern. Pattern belongs in the is column, so it is a concept. What about dolphins eating fish? Where do you think this one goes? If you think is not, then you're on the right track. It belongs in the is not column because it is a non-example of a concept. The next one is Amazon rainforest. This one also belongs in the is not column. Are you starting to see the differences between the words in the is column and the is not column? I want you to start working on your list of common characteristics or attributes of concepts if you haven't already. What about chemical property? Where would you place this one in the chart? All right, I see lots of is's coming into the chat. That's great. It should be in the is column. It is a concept. Harmonic? What about this one? Yep, it is also a concept. So it goes in the is side. And finally, we'll add one more, carbon dioxide. What do you think about that one? All right, we've got some is nots. Definitely not a concept. you are correct. And you can see it's in the is not column of the chart. So I would like you to take a moment now and think about and have a look at all of the concepts that are listed in the is side of the chart. Write a list of common characteristics or attributes of all of those concepts. So we're trying to understand the attributes of the word concept. Okay? What makes things a concept and what makes everything in the right-hand column not a concept? And then pop some thoughts into the chat when you're ready. I can already see some coming in. Transferable sticking out as one that's coming up quite a few times, and not transferable for the non-examples. Timeless, they're broad, universal, not locked into time. Great. So broad or universal, not locked into time or place. All right, fantastic. I can see that you've come up with lots of the attributes already. So let's have a look at the definition of a concept. A concept is an organizing idea or a mental construct. Concepts are timeless, universal, abstract to different degrees, represented by one or two words, and have examples that share common attributes. I saw lots of those things in the chat, so I think everyone's got a really good understanding of what the word concept means. Concepts allow us to organize, make sense of, analyze, and interact with information in a really complex world. Erickson, Lanning, and French define concepts as mental constructs drawn from a topic or a process that transfer to new situations and contexts. Concepts could also be thought of as the building blocks of thought. Concepts create the natural bridge between the mind and the world. Concepts are used by our brain to allow us to automatically relate our experiences in the world to a set of mental categories, and thus they reduce the need to constantly relearn things. So let's think about an example. Think about the last time you were walking through a garden or a park. You may have noticed that roses grow pointy projections called prickles. They grow them as an act of self-defense to deter herbivores from eating the leaves that the plant puts so much energy into making. Have you ever visited a jungle? You might have observed a majestic tiger in its natural habitat. Tigers don't have those beautiful stripes just for decoration. They are very advantageous for lurking in shadowy jungles. Stripes camouflage tigers in the shadows cast by tall trees and branches, making them almost invisible to unsuspecting prey. We connect both of these real-life examples to our understanding of the concept self-defense adaptations, even though both examples are quite different and happen in different places. But our understanding of self-defense adaptations enables us to recognize new instances, even if they aren't directly related to roses or tigers. So, how do different sized concepts ensure breadth and depth in a science curriculum? You might have noticed that some of the concepts from the is not chart seemed different in size, some more broad or some more narrow.
So, for example, force is more broad concept than fission. It can be helpful to refer to concepts as more macro in size and others as more micro in size, moving from broader macro concepts to more specific micro concepts. Macro concepts may be so broad they transcend subjects and disciplines. For example, change, form, function, and system are very broad macro concepts and are the most transferable to new contexts and situations. The key concepts, for example, from the IB programs, are all examples of macro concepts. Macro concepts also include the broadest concepts within a discipline. They are often used as topics or subtopics under which micro concepts are framed. In science, cycles, living things, periodicity are also macro concepts. Micro concepts like proton, metamorphosis, and conduction, they represent conceptual knowledge within a specific discipline. They provide conceptual depth and support students in developing disciplinary expertise. So, knowing that concepts are more or less broad helps us find relationships across them. In concept-based inquiry, we can plan students' understandings of both macro and micro concepts, which helps us use us plan for both breadth and for depth, and leads to a rigorous science curriculum. Here's an example of some of the macro concepts that are many macro concepts found in science. So relationships, structure, interdependence, and function. They're the most transferable to new contexts or situations. Now, if we dive into more specific or macro concepts within the macro concepts of structure, we will explore concepts like adaptation or animal features, feeding features, or beak. I want to just pause really quickly to note sometimes there's a misconception that we teach from the macro down to the micro, but that isn't always the case. For example, if I was going to be doing a lesson with second graders on this, I'm not going to start with adaptation. I'll actually start with beaks, and we'll look at lots of different examples of beaks. I might then move on to talk about teeth so that we have this better understanding of feeding features. And we'll move up that way to better understand adaptations after we've talked about furs and tail and different aspects of those animals. And other times you might work down from the top. So it's not necessarily a structure in how you're going to teach. So Rachel French and Carla Marshall use the analogy of a nesting doll to help understand the difference between macro and micro concepts. You can see micro concepts are nested within the macro concepts. And as you see, there are other micro concepts nested further inside as well. The higher you go in conceptual hierarchy, the more transferable concepts become. Here are two examples that are related to the broad concept of system. On the left side, this concept's become more and more focused, almost as if we're even like zooming in closer and closer. Human body systems, organ, tissue, cell, organelle. On the right side, the concepts also become more specific, nesting inside the slightly more broad concept each time. You can see the growth in complexity. System, human body systems, reproductive system, puberty, ovulation, meiosis. So remember how I was just saying that we don't always start teaching from the broadest concept and work our way down? Well, if I was a fourth grader or a fourth grade teacher and I wanted to start teaching about human body systems, I might start talking about the organs in our body. And I won't jump into the tissues or cells. I might not even talk much about those as fourth graders. So I might just stick with that one section. But also looking at that right side, you can see how as a student that's going to study meiosis, I need to have an understanding of those concepts that come before to really have an understanding of how, say, ovulation and puberty are connected. So when planning for concept-based inquiry, it's important to reflect on the complexity of unit concepts and the age and the prior knowledge of our students. So we meet the needs of all of our students the best way we can.
Of course, in concept-based inquiry, we don't only identify and plan for the teaching of concepts in isolation, but more importantly, how those concepts are connected or related. We want students to understand and articulate the complex relationships that exist between the concepts. The structure of knowledge, developed by Lynn Erickson, explains how facts provide the foundation for transferable understanding. Erickson calls these understandings generalizations and defines them as two or more concepts stated in a relationship. You may be more familiar with some of the other terminologies, like conceptual understandings, or big ideas, or even central ideas or statement of inquiry in the IB programs. But they're all essentially describing the same thing. Let's have a look at some examples of generalizations so you can see what these relationship statements look like. Thinking about the concepts related to system that we just looked at earlier, here are some of the conceptual understandings students may be working towards developing. Students understand that each human body system interconnects and relies on other body systems and their organs. Students understand that organelles perform specialized functions within cells to maintain life in organisms. And students understand that cell membranes envelop cells in a selectively permeable structure and protect the internal environment of cells. Notice how the complexity of these generalizations increases as we move upwards through the grade levels. Each of these statements are conceptual understandings because they state the relationship between two or more concepts.
All right, let's focus back on just concepts for a moment. Here's another way to visualize the different size concepts. This web shows just some of the concepts that might be involved in studying forces in motion. In this example, consider how each of the micro concepts would sit within the macro concepts of force or motion. Take a moment to look at the web. Like, which concepts do you think are more broad, that are the most transferable to different contexts? Which are more specific, adding disciplinary depth? Why? When planning for a rigorous science curriculum, using a tool like this web to identify macro and micro concepts appropriate for your level of students will aid you in, oh, my screen just went blank, sorry. So sorry. So when you use a web like this, it's going to aid you in developing what is an age-appropriate unit for your students. It's going to also help you identify the conceptual relationships you ultimately want your students to understand. When working towards generalizations, not only do we want students to consider the relationships between micro concepts, but also between relationships between macro and micro concepts. This builds the breadth and depth in your curriculum. And remember, we are not saying that facts and knowledge aren't important. They are the foundation for which conceptual understanding is built. So if we plan with conceptual understanding as the learning target and ensure students are exposed to rich and meaningful example, students will better be equipped to transfer and apply their understanding to new contexts and situations. So thinking about generalizations again, here are some examples that students might have formed from looking at the concepts on that concept with force and motion. Students will understand that pushing or pulling an object can change its direction or stop and start it. The sum of the forces, students will understand that the sum of the forces acting on an object determines the object's motion. And students understand that the downward force of gravity accelerates projectiles downward from their otherwise straight line, gravity-free trajectory, causing them to travel as a parabolic trajectory. Notice again that growing specificity. Okay,
now it's your turn to do some exploration of macro and micro concepts. So I hope you've got your pen and paper ready. I want everyone to think about the concept ecosystem. And now we're going to have a go at writing down some of the concepts that are related to ecosystem that you would typically explore in your class or grade level. So it actually doesn't matter which grade level you teach, you're going to still approach this with your perspective. Don't forget to think about macro and micro concepts. You can either choose to use the concept web idea that we just showed you with the forces in motion, which is shown on the left of the screen, or you can use the arrows that we had to begin with, where you're going to put the more macro concepts at the top of your page and the more micro concepts at the bottom. You can pick, it doesn't matter how you organize it. We'd like you to take a few minutes to really have a go at pulling out lots and lots of macro and micro concepts to do with ecosystem. And then if you're feeling really brave, we'd love you to take a photo of what you draw and pop it in the chat. Okay, so we're going to give you a few minutes to work on that.
You have a timer there, Jess.
Sure. I know, I've got to make sure I give them enough time. Rachel, are you drawing your concept web? I want to see your example. All right, we've already got some in there already. So just some people who have written lists, which is also fine. That's really great. Once you've written down 3 or 4 concepts that are related to ecosystem, I want you to challenge yourself to go deeper and more specific. So think about, if you were teaching these in the classroom, where would you be going with this? What are the micro concepts that are going to really dig deep into ecosystem at your grade level?
Or go the opposite way. Can you go further? Can you go wider, like broader? Is there another piece that you're thinking in that connection?
All right, I haven't seen anyone who's put an actual picture in yet. Is anyone going to be brave enough? We would really love to see a little sketch in there. If you can, I know it's tricky with Zoom sometimes to put pictures in. All right, so we're seeing lots of things in here where people are going in all sorts of different directions, which is really awesome because realistically, teaching ecosystems will look very different if you're a third grade teacher from how it might look if you're an IB biology teacher or ESS teacher. So we've got biotic and abiotic factors, food chains. We've got interdependence, symbiosis. What else? Habitat. What did I miss at the top? Carnivores, energy. Yep. Food relationships, food feeding relationships, symbiosis, decomposes. All right, lots of really great ideas. Food webs, natural and man-made things, adaptation. There's so many different ways this could go.
And I also see a few macro concepts like biome, biosphere, energy,
and balance, like really big ones, which is really great. All right,
but so how did you? It's like, how could you talk about an ecosystem without talking about balance, right? Like it's really strong connection between.
Yeah, and then so talking about a microsystem, and then the macro ones being interactions. Really great stuff going in there. So look over your concepts now, and I want you to consider how they're connected. Can you imagine some of the experiences that might happen in your classroom where students are exploring factual examples of the concepts that you just identified? What might be happening as they investigate relationships between concepts? Oh, I've seen some webs. Thank you for sharing. Oh, good job, Rachel. I see your web. All right, so really... Sorry, say again, Rachel.
My camera's over in the house, so it's the best that I can.
Okay. So this is a really useful exercise to really make sure we're digging down. Oh, I see another one being held up too. Thank you. To make sure that we are covering that breadth and depth that we really want. And this is a really good exercise to do with your team at the beginning or the outset of the planning for your unit. I know that there's a lot of factual knowledge in science with any topic of study, but developing deep understandings of concepts and looking for patterns and uncovering connections between concepts leads to transferable conceptual understandings built on a foundation of knowledge. And with that understanding, students will be able to draw on factual examples that they've explored with you and apply their understanding to new contexts and situations, theoretically reducing the number of factual examples that actually need to be covered in the first place. An ecosystem is certainly a macro concept that will be repeatedly visited throughout a learner's K-12 journey, and most likely across most science disciplines and very often in every single school year. The increasingly specific micro concepts that you have been identifying in these great webs that they're taught to students as we move up through the grade levels, that's what's adding the depth into our curriculum. We don't want to be teaching the same macro concepts or the same level of concepts every single year if we're not being able to add depth and explore new relationships that are coming up as we move throughout the schooling.
I just want to add a little caveat. As we did mention, this is it reoccurs in their K-12 journey. If we have any lower elementary teachers here, they might be going, I'm a kindergarten teacher. I don't teach ecosystems. But you teach some of those concepts underneath it, even just living things, non-living things, needs and wants, and how we take care of plants and animals. Right. So those are some of those concepts that you might not ever use the word ecosystem, but you're using many of those micro concepts under it.
And thank you to all the people putting the webs in. I'm so glad to see lots of brave people showing their thinking.
We're going to definitely have to save some of those.
Yes.
So another question we wanted to ask is, how are scientific skills planned for in a rigorous curriculum? You might have noticed that so far we have really focused on knowledge or the content side of science concepts, but we know that students will also need to learn to think and act like scientists. They will need to understand the skills of the discipline. So how do we encourage rigor of scientific skills in a concept-based inquiry approach? We continue to use macro and micro concepts, but now we focus on concepts related to the process of scientific inquiry. So question here is question, data collection, or argument. Those are all examples of broader, more macro concepts. We want to intentionally think about these skills and what they would look like at different grade levels. We would identify the micro concepts that would be most age appropriate. For example, here are some micro concepts nested within data collection: qualitative and quantitative data, variable, graph, trend line, error bar. Notice that none of those concepts are tied to a specific piece of science knowledge. Rather, these concepts are applicable to all areas of science and are based on things we do as scientists. Jessica and I have both experienced teachers exasperately saying things like, "My middle schoolers don't know anything about graphing. I guess I'll just have to reteach it all." When you feel like you're always reteaching a skill, there isn't much time to actually build up that skill. Teaching through concept-based inquiry approach helps students to transfer their understandings about skills to new context, as our brains are much more efficient at storing concepts rather than what might seem like random skills or a piece of knowledge. We've also heard teachers say things like, "My students will learn science skills this year when we're doing that lab in that one unit." Or we've heard maybe the opposite: "We cover all the science skills every time we do a lab." Using macro and micro concepts to plan and map out the understanding of science process skills over the year and through the grades helps teachers to avoid the we did it once, check, mark it off the list approach, or maybe the other side of we just do it all of the time and hope it sticks approach. So let's look at an example. Here are some of the concepts related to the skill of modeling. When you write that as the concept, you just would say model. Picture how students would be able to create and use models in science at different grade levels. Can second graders create and use models the same way as 8th graders or 11th graders? Can you see how they are not at all learning the same thing about modeling? Young students may draw simple pictures of objects that they can see, while high school students are going to be creating multiple types of models: diagrammatic, mathematical, digital, to explain and predict phenomena. As educators, we need to be adding depth and complexity to skill-based concepts by exploring the how and why of what we do as scientists. Here are a few of those examples of what a process generalization in science would look like. These ones are all about modeling concepts from the previous slide. The students may articulate their understanding of modeling, such as students understand that scientists can create models, including diagrams, to show and explain relationships. Students understand that scientists use models to test cause and effect relationships of natural or design systems. Or students understand that scientists develop models to represent input and outputs of systems at unobservable scales. Notice that increasing specificity? Yep, as we use those micro concepts and talk about the relationship to modeling.
All right, we've already talked a little bit about conceptual understandings or generalizations. So now let's consider this question. How does the number of conceptual understandings in a unit of study support a rigorous curriculum? Concept-based inquiry units have 5 to 9 generalizations, including a combination of both knowledge-based and process-based generalizations. And we've seen examples of both now. Students are very capable of understanding more than one conceptual understanding per unit. So let's plan for multiple opportunities for them to generalize. Because science is a knowledge-based discipline, we expect to have more knowledge-based generalizations than process-based generalizations in a single unit of study. And carefully planning out your macro and micro concepts will help you construct multiple generalizations. So what you just did before when you began brainstorming all of those macro and micro concepts within a particular topic that you were going to study will help you come up with these conceptual relationships. I know this might be a big departure from what some of you are used to, so let's have a look at a couple of examples of how this might look. Imagine you're doing a unit with a central idea or generalization. Students understand that people develop technology to help communicate with others. This is going to guide the entire course of your 6 to 8 weeks of learning. Now instead, let's imagine the same unit where students are actually working towards 6 generalizations. Have a read of these generalizations. Can you see all of the micro and macro concepts and the relationships between them? Can you see mostly knowledge generalizations and one process generalization? So fewer process because we're a knowledge-heavy subject. Can you imagine how much richer the learning would be with all these additional understandings to work towards during a 6 to 8 week period? Here's another example. Perhaps you're doing a unit with a statement of inquiry or generalization of students understand that atoms are the building blocks of life, but are unobservable with the human eye. By only having one generalization, we're essentially robbing students of an opportunity to think deeply about multiple connections between the many macro and micro concepts within this topic. So instead, let's imagine this unit where they're working towards this time 9 understandings. Have a little read through. Notice that the first 7 generalizations all have to do with knowledge, and the last 2 are to do with process, thinking about the things we do as scientists. Again, as you're reading through them, notice the macro and micro concepts. Can you see how planning for students to articulate more understandings will lead to depth of understanding and thus rigor in your curriculum? Your students are so capable of understanding a multitude of concepts and their relationships during a 6 to 8 week unit. So don't take that away from them. All right, let's switch gears a little bit and consider the other side of rigor. How does concept-based inquiry promote student ownership of learning and enhance communication and thinking skills? Let's imagine that you've just spent the past weeks exploring photosynthesis. You've worked on defining photosynthesis, deconstructed the photosynthesis equation, described why photosynthesis is important, and you've begun investigating the limiting factors of photosynthesis. You've prepared a great lab for students to test the effect of temperature on photosynthesis. And you open with, today's lab will prove that very high and very low temperatures can limit the rate of photosynthesis. Students then go on to conduct the experiment, changing the temperature of water, recording the number of bubbles of carbon dioxide each test produces, drawing a graph to represent their findings, only to find out that exactly what you told them at the start of the lab is in fact true. Very high and very low temperatures can limit the rate of photosynthesis. Or you could ask a question to begin the investigation. How does temperature affect the rate of photosynthesis? Your students will again carry out the same lab. They'll record their findings and draw a graph. But this time you're asking more questions. What did they observe? What patterns or trends did they see in the data or graphs? And if all those trends, were those trends all true across all of the examples they noticed? You guided their discovery of the patterns in trends so that they could ultimately answer your original question using their own thinking. The first example I gave was one of a deductive approach to teaching. The teacher told the students what they were going to understand as a result of the lab they were about to do. They carried out the lab dutifully, and sure enough, they found out that the generalization was true. Their results supported the generalization the teacher told them. And this leads to the students validating the teacher's understanding. The second example I gave, on the other hand, was one of an inductive approach to teaching, where students were invited to investigate factual examples, look for patterns and connections in the results, and articulate their own understanding of the relationship between the concepts. The students were ultimately responsible for their own thinking. Although both approaches involve interacting with both factual and conceptual levels of thinking required to induce deep understanding, the deductive method does a lot of the thinking for the students. An inductive approach to concept-based inquiry encourages our students to be independent, critical, and competent thinkers, which are vital components of a rigorous education. When students are allowed to construct and articulate their own conceptual understanding, those magical aha moments happen. Their faces light up. They finally get it. They own that learning. What an exciting place to be. Ooh. I know, I was so excited. Sorry, Andrea.
I know. It seems like a lot though. It's sometimes I have these 5 to 9, I'm going to teach it inductively, but it's really those aha moments that are so exciting, right? In our classroom. And And it's almost like you can unlock the how to do that, how to get there. So as we're going to wrap up today's session, I can't believe it's already getting towards the end. Let's reflect on the 3 statements that we showed you at the beginning of the presentation. Just take a moment, reread them, and notice if your thinking has shifted or changed in any way. Or maybe you have some more evidence to back up what you were already thinking. Feel free to put any of your little reflections and thoughts into the chat. I'll give you about a minute just to sort of think about that. All right. So can you see how a rigorous classroom does not mean memorizing tons of facts? How it doesn't just mean harder. In concept-based inquiry, facts in a context are used as a foundation for building conceptual understandings. We deepen understanding through teaching increasingly specific and complex concepts. And as students take ownership of their learning and understanding, they develop as clear communicators, problem solvers, and critical thinkers. We want to thank you so much for joining us today. You might have a few questions that we have some time left to answer. So we're going to hand it back to you, Rachel, and maybe help us out with that.
Thank you. And thank you both for sharing that. I love seeing examples in different subject areas and seeing how it comes together. There's definitely some very rigorous understandings. I hope that for some people who are teaching some of these units in their classrooms, they've been able to almost swipe some of those understandings that they can put straight into their units. So it's great to have those practical examples. Also to have the strategy of using the is not in your own lesson. So you did that today with concepts, but it can be used as a strategy to build an understanding of any concept. So in the chat right now, I'm going to put in a link to the course that Jessica and Andrea have developed on for concept-based science. I actually just realized, and this isn't something that we planned at all, but the early bird registration for that course, it says on my screen at the moment, closes in 1 day and 3 hours. So if you want to take advantage of the early bird registration, make sure that you do that tomorrow, but registration is open for a little longer if you can't get that through by tomorrow.
And the course launches on April 15th and runs for 6 weeks.
So that course is online, and the lovely thing about those online courses is with all of our professional learning international courses, we wanted to make those courses very practical. So it's led through video modules that you can watch at any time that suits you. And then either Jessica or Andrea will be joining you on the weekend for an hour to have an interactive session where you can also come along with your own questions. And in those sessions, you can share some of your thinking. And then at the end of the course, you will be able to submit a unit planner and get feedback either from Jessica or Andrea on the unit that you've designed. Alrighty, if you've got any other questions, do feel free to pop them in the chat. So far, I've got one here for you that was put in the chat a little while ago. So Gina's asking, our school is a PYP school, but we're not able to deliver all of the science concepts through our program of inquiry. How do other schools address this? So if you've got any ideas, feel free to put them in the chat. Otherwise, I'll hand the question over to you, Andrea, because you've been working at a PYP school for many years. Do you want to share your thinking around that juggle of the POI and the subject area curriculums?
So I want to comment. Someone else did. Megan DeCourt. She responded that they have the same problem at their school, and they do have science as standalone. And I believe the IB, the PYP, does it allows that now. Previously, it hadn't been somewhat allowed. It had to always be integrated. So that is the option. Is you could have some standalone. I see lots of schools take on sort of maker spaces as that solution, or a little fun like a science lab space in the PYP. But it's true. One of those big difficulties is looking at those transdisciplinary themes. And often you're like, it's the how the world works unit. That's our science unit. and how we organize ourselves. There's another one. So sometimes or sharing the planet. That's the big one, right? Where we do all of our biology and sharing the planet. So it's a common problem that we do have throughout the PYP, and it goes back to really mapping out as a school the concepts. So you want to make sure that if you're going to be looking at biology, is it really building in rigor throughout sharing the planet? Is that where we want to spend, all of our sciences in biology? Are there some other concepts that we're going to be able to use and bring in that we could use those units in other ways? So it goes back to that big planning phase of sitting down, mapping them out, even using like NGSS to go back and think, where have they grouped things together? And I think one of the really big important pieces is to not shove things in. It does not give any rigor to science, to the knowledge and skills, if you just kind of shove it in because there's sort of a link. So that's actually, I feel like that does more damage, because kids just sort of like get this random thing that happens and it doesn't build their conceptual understanding. So being really clear in the science units that you choose and clear in how those develop so that you don't have repetition. That's my biggest suggestion.
Yeah, I've noticed that when I've worked with schools, it really depends on the national curriculum that they're working with. So sometimes curriculums will spiral where they'll teach almost the same unit 3 years in a row. And so I've also worked with IB schools in those situations where the solution is to say, we are going to cover all of the content that is in the curriculum that we're covering it, but we won't always cover it in the same year. So those kind of 3 years worth of, light and sound, or those 3 years worth of ecosystems will get put into one much more rigorous unit, and then that frees the other year groups up to spend more time on something else, because there are curriculums that really are expecting sort of a new science unit every 3 or 4 weeks, and that's not realistic to be able to do justice to science in that way.
I wanted to add, Rachel, when you were talking about that, one of the things that I do see, though, when sometimes people try to do that, let's take them all and put them in one, is they'll often they're not looking conceptually, and they'll take things that students aren't ready for from a higher grade and bring it down. And so you just got to be really careful when you do that.
Yeah, absolutely. That is very valid point. All right, I've got another question that comes from an MYP teacher. So the question is, in an IB MYP context, units are constructed with a single statement of inquiry and then with inquiry questions. I like the examples of understanding that you used. Can these be phrased as questions in the MYP unit planner? Jessica, what would you recommend?
Sure. So actually the question actually really applies to PYP and MYP, because in the PYP we work with a single central idea. Well, we work with that as the requirement, and in the MYP as a single statement of inquiry. The biggest thing to remember is that both the central idea and the statement of inquiry are actually understandings. They're actually generalizations that we want students working towards. So the additional understandings or conceptual understandings or generalizations that we recommend in concept-based, the 5 to 9 per unit, would include that statement of inquiry as one of the understandings. And then the other 5 to 9 would also be part of that unit. So if you're working in your planner, there's usually space right underneath your statement of inquiry to actually insert all of the additional understandings. But we still recommend that they are written as statements of understanding, which means 2 or more concepts stated in a relationship. And then for each of those understandings, you're going to develop your questions. So you've got the space in your planner to write your factual questions, your conceptual questions, and your debatable questions. But we actually say that each of your generalizations needs to have a set of questions that goes with it in order to drive the learning towards that understanding. So we like to think about those 2 things quite separately. So understandings or generalizations can be listed under the central idea or under the statement of inquiry, and then the questions that match each of those generalizations would need to be separate. Yeah. Rachel, I also just saw another, did you want to weigh in on that at all, Rach?
Nope, you've covered that off pretty well. Okay. I can see one in the Q&A. Is that the one you're referring to?
Yeah, that was. I was typing at the same time as trying to speak, but that didn't work out so well.
No, let's share it with everyone out loud. So the question that was over in the Q&A chat is there a way to figure out which concepts are more micro than others? The macro are quite obvious. So Jess, you were typing on that, so you've obviously thought about your response.
I was trying to think and talk and type. That was very, very challenging. So, like you said, macro concepts are sometimes more obvious because they are the most transferable to multiple situations and contexts. Remembering that macro concepts might be the biggest concept within a particular discipline. So it might be the biggest concept within biology, or it might be the biggest concept within music if you're doing another subject. But we also have macro concepts that transcend disciplines like change and system and balance and things that are just massive and can be looked at from multiple perspectives. When it comes to working out which ones are more micro, it is a little bit trickier, and it will really depend on what grade level you're working at as to what you're going to be looking at for digging down. But I like to think about it like if there's a concept that is kind of a bigger framing concept than something I'm teaching underneath that we need to explore underneath that, then you can sort of work out how macro or micro they are. But it's not a super important thing to be able to order them directly, like from top to bottom. Like you don't need to say this one's more macro than this one than this one. The idea is that you can identify that there is a range of macro and microness, if you'd like to say it that way, and that attending to those different levels of macro micro is really important and is also intentional in what we do. So sometimes we're digging right down into those tiny little micro concepts and the relationships that live within inside those two things or three micro concepts. But sometimes we want to think about how a cell overall is contributing to a system. So we're talking quite micro and quite macro at the same time. And this idea that we can kind of think about a scale of macro microness is helpful for connecting those ideas, both big and narrow, when it comes to that range. Andrea, do you want to add some?
Well, I think it's that idea of you don't need to know necessarily which one's more micro, but you can be thinking, which one does my student need to understand before they can reach the other one? And it doesn't always mean that one is smaller than the other. So it goes back more to how does that look in your classroom?
Yeah. Like when we were trying to write the examples of those, right, Andrea, we were actually like, oh, which one's more? Oh, no, that one's more micro. And we were moving them up and down until we realized actually that wasn't really the point of it. The point was really to show that there are some concepts that are more micro in nature, which add that specificity and complexity and build throughout the years, and that some are more macro.
Which might be why so many of us use the web, because it's really hard to also just focus, right?
On a straight line.
Yeah.
There's really not a right or wrong answer when it comes to macro or micro, and something that would be macro in one context is more micro in another context. So don't get caught up in trying to decide if it's macro or micro, which is most micro, as Andrea and Jess have been saying. Just understand that all are important in the curriculum. All right. Somebody asked a question about the recording. We will send out a recording. It's only available for a limited amount of time. The reason that we share them for a limited amount of time is we have found that if we share them and you think you have access forever, you'll never watch them. If we share them for a limited amount of time, then there's a really high number of watches. So that's why we share it for a limited amount of time, but we will send it out tomorrow. So if anyone missed it, or if you went, there were lots of good things and it was going too fast, I didn't get to write it all down, we will send out that recording tomorrow. So I think we've covered the questions that came through. Thank you everyone so much for joining us. It's a great pleasure to be able to connect with you all. Again, I've just dropped the link in to the chat if anyone's interested in finding out more about the course that we have coming up with Jessica and Andrea. That link is there. Do try and take advantage of the early bird rate if you can. That closes at the end of tomorrow. So thank you all, and we'll see you again next month, or we'll see some of you next week at the conference.
Thank you for joining.
Yes. Anybody
at the conference. See you in Singapore.